Vacuum thermal evaporation is used in research and industry and is by far the most used technique to produce organic light-emitting diodes.
The main advantage of this technique is the production of high-quality and easily reproducible structures which can be translated into high-efficiency devices.
Begin with two patterned substrates. These 24mm by 24mm ITO-coated glass substrates were patterned with 4mm stripes. Rinse each substrate with acetone for about 10 seconds. Then, dry them with a nitrogen gun. Next, submerge the substrates in a container of acetone. Place the container in an ultrasonic bath for 15 minutes. When done, transfer the substrates to a container with isopropyl alcohol. Don't forget to signal both containers on the side that is facing the ITO films. Place this container in the ultrasonic bath for another 15 minutes. After the second ultrasonic bath, remove the substrates and dry them with a nitrogen gun. Place dry substrates in a platform suitable for a plasma cleaner. Before proceeding, ensure there are no residues or smudges on the substrates. Use a multimeter in the pad areas to ensure that the ITO is facing forward. Next, go to an oxygen plasma cleaner and place the substrates ITO side up. Clean them for 6 minutes. After plasma cleaning, prepare for evaporation steps. Attach the substrates to the substrate holder with mask A, used for the evaporation of all organic layers, making sure the ITO is facing downward. If in doubt, test again with the multimeter. Have a second mask ready, mask B, for the evaporation of aluminum. Then place mask A onto mask B. Take the substrate holder and the masks to the antechamber of the glove box where the evaporation chamber is. Next, prepare the different organic powders and other materials required for this device and add them to the chamber. When working in a glove box, before adding something new to the chamber, evacuate and refill 3 times the antechamber to avoid any oxygen from entering the glove box. Place mask A on the deposition shelf. Place mask B on an alternate shelf. Finally, place the organic powders into their respective areas. Then, close the chamber and initiate the vacuum procedure. When the pressure is low, start the flow of cooling water and substrate rotation. This is a representation of the substrate top view and cross-section of a pixel at the start of the evaporation sequence. Deposit 40 nanometers of preheated MPB when its evaporation rate is around 1 angstrom per second. After the MPB crucible cools, co-evaporate 18 nanometers of preheated CBP and 2 nanometers of preheated DPTZ-DBTO2 using different evaporation rates.
The co-evaporation step is crucial to ensure good device performance. The rates of co-evaporation should be maintained throughout the procedure to make sure the ratio is the same across the entire layer.
Next, evaporate 60 nanometers of preheated TPBI at about 1 angstrom per second. Then, evaporate 1 nanometer of preheated lithium fluoride. When the lithium fluoride crucible is cool, place mask A onto mask B and deposit 100 nanometers of preheated aluminum at about 1 angstrom per second. After venting, remove the substrate from the evacuation chamber. This is how it appears after the evaporation steps and viewed through the glass substrate. There are 4 pixels. In this schematic view, note that the use of mask B with different pad sizes allowed for pixels with 2 different sizes, 2 by 4 cm square and 4 by 4 cm square. Move the substrates to an encapsulation stage. Remove them from their holder and place them on the stage with the evaporated films facing forward. Disperse resin to draw a square that encompasses all of the evaporated pixels. Next, place an encapsulation glass on top of the resin to secure it on the device. When ready, UV cure the substrates according to the resin instructions.
Encapsulation will guarantee that the device does not degrade with oxygen or humidity, in the end ensuring its quality.
Characterize the OLED using an integrating sphere. Before characterization, inspect the OLED. Check that the ITO stripes outside of the encapsulation glass of the OLED are clean. Place the OLED in the integrating sphere. Confirm that the anode is connected to the ITO pad and the cathode is connected to the aluminum pads. When the connections are made, close the integrating sphere and proceed with characterization measurements. This plot has the current density as a function of voltage in black. It also has the luminance as a function of voltage in red. The voltage at which light is first detected is 4 volts. At high voltages, device degradation becomes apparent with the drop in luminance here appearing at around 13 volts. These plots allow comparison with other devices. This is the external quantum efficiency as a function of the current density. Here are the luminous efficiency in black and referred with the left axis, and the current efficiency in blue and referred to the right axis, each as a function of voltage. Finally, this plot of emitted light as a function of wavelength for different voltages demonstrates that the wavelength of peak emission does not change. This suggests the device is optically stable.
While attempting this procedure, it's important to remember that all the materials and substrate surfaces are sensitive to the environment. Parameters like temperature, humidity, dust, and even oxygen influence the device performance.
After its development, the vacuum thermal evaporation technique shown here paved the way for the current generation of OLEDs. In this generation, we explore different emitters and their application in device stacks for flat panel displays and smartphones.
This protocol shows a simple but effective way to build device stacks with a small number of organic layers that still allows the production of high-efficiency systems.
Don't forget that working with solvents used for cleaning can be hazardous. Precautions such as the use of appropriate gloves, lab clothing and protective glasses should always be taken when performing this procedure.